Okay. So, good morning. We're going to get started. My name is Chris West. I am the president of the Passive House Alliance local Vermont chapter, and I'd like to welcome you all here today for our presentation and a webinar for our December meeting. Today we have Steve Spatz from RedBarn Design and Build, a Vermont company, and he's going to be giving a presentation on a retrofit that he's doing here in Vermont with focus on trying to get close to a passive house or high efficiency building, and all very excited and glad that Steve could come here and give a presentation on this. And please join me in welcoming Steve Spatz.
Thank you, Chris.
You're welcome.
Got a big crowd. Hope you're all very focused. All right, again, I'm Steve Spatz, and my company is RedBarn Design and Build. We're out of Shrewsbury, Vermont. We've been established a business about 10 years ago, and focusing on residential construction and light commercial. We became a home performance with EnergyStar contractor about 4 years ago, and that's been a major focus of our business over these past 4 years. And now, over the past about year and a half, now that the market around here has turned a bit to the back to having some opportunities for new construction, we're taking a lot of the experience and techniques and building science that we've become quite versed in our retrofit work of existing homes and applying that to new construction projects and remodels. So what I'm going to be presenting on today is a project that we're currently in the middle of in Mount Holly, Vermont, which is an addition to an existing home and a complete deep energy retrofit of the existing home as a part of that addition. So start to get into it. Good. So this is where we began. This is the trip residence in Mount Holly. Simple cape. The plan was to be adding, basically doubling the square footage of the house. Details: the house was built in 2000, and the addition for the home was designed by MBF Architects in Rutland. We've been working with them pretty closely over the past many years. There were no construction specifications as a part of the addition specs. It was really just a design that was developed by them, and we developed the construction specs and incorporated the retrofit aspects to the existing home as a part of the project. So existing square footage is 1,140 square feet. Additional new space on 2 floors of 875 square feet. The house, a little bit of history about the house. I don't know personally the person who built it, but I know of him and know that he built the house himself in 2000 and built it for about $50 a square foot. Now, with that in mind, it was not shoddily built at $50 a square foot, but there were some corners that had to be cut in the process, and those became evident as we got into the project. But a solid heating plant that we begin with. There's radiant heat on the first floor of the existing house, spaceport to the 2 bedrooms on the second floor. And that, at this point, for the homeowners, is used really as their backup heat. There's a small wood stove in the middle of the first floor that has been their primary heat. No, that is not the proper model number for the Brown ducted HRV. I don't think anybody would come across the AHA, FAHA model. That does not substitute properly at the time of putting together the presentation here, but there is a ducted HRV existing with the the house that we are using to branch off of in the addition. So the new spaces are being branched off the boiler, radiant distribution throughout both the second floor and the first floor. We have a polished radiant slab in the sunroom. Plans will be coming up here in a second for you also to take a look at. So, and unfortunately, as I said in the next bullet point here, my heating contractor, who I trust quite thoroughly and appreciate his opinion on everything, and has been very good about keeping up with changes in equipment and flexibility of systems. Basically did the CYA move of saying to the homeowner, as I proposed, we put in a mini split for the new spaces because knowing that they're using that wood stove as their primary heat, and what they've already experienced as far as comfort and fuel use within the house, that a mini split would do more than enough to keep up with the demand of the new spaces. But my heating contractor said, yeah, but they don't work below 0 degrees, which I think everybody here realizes that is not the case. And for the primary use of that space, that mini split would be more than adequate for what they need. So we're still trying to ease that into the project scope, but as I stated, it's the radiant heat throughout the building. The two bath fans that will be existing in the house, we are installing backdraft dampers in those to prevent as much as we can any air infiltration occurring through that ducting. And we will be adding supply air to the wood stove that does not exist at this point. So this is the general floor plan of the house, the first floor. The new spaces are highlighted by the white wall area. So the 16 by 20 living room on the south-facing side of the house, and a 12.5 by 12.5 foot sunroom single-story addition on the back of the house. Second floor, this, again, the existing house is a cape. So there are 2 bedrooms on the second floor, a very narrow hallway. The second floor plan was basically a master bedroom and bathroom addition with a laundry area. Same footprint as the downstairs 16 by 20, and also incorporating the about 4-foot area of the knee wall space that existed on the second floor as a part of the additional second floor square footage. And these are the elevations for the new section. So we developed, as a part of the construction specifications, a plan to try to achieve maximum insulation, maximum air tightness for the new structure. We were able to have the flexibility in the budget and the willingness of the homeowner to be able to incorporate these same approaches to the existing building shell. So the current building had vertical shiplap siding with tie bar beneath it. None of the windows were flashed or detailed in any way, shape, or form. They started pulling off the siding, and the window flanges were just nailed directly to the OSB. The house wrap was butted to the windows themselves, so we also found plenty of mulched OSB behind the siding and the window rough openings as we've been taking things apart. But that was all removed. We're taking the same approach to the existing house as we are to the new. We're not touching the wall cavities of the existing house at all. The existing cavities are 2x6 construction, fiberglass. The roof plane is 2x12 rafters, fiberglass. So the wall cavities and the roof cavity of the building remain, but we are adding 3 inches of rigid mineral wool to all the exterior wall areas and 3 1/4 inches to the roof plane. The insulation plane of the second floor of the house was the sloped portions of the ceiling and then the attic flat. We're changing that boundary to be the fully enclosed slope ceiling for the existing house. Basically, we're removing the insulation boundary from the flat ceiling, which is only 4 feet, if that, and moving that insulation up into the slope ceiling and having the full connectivity of the rigid mineral wool roof deck to that slope ceiling plane. The exterior of the building is being treated the same as the new, with vertical strapping, 1x3 strapping being put over the exterior insulation, the drainage plane, new hardy plank, orange exposure hardy plank siding over top of that, and 1x finger joint line trim. The existing roof for the house was a corrugated metal roof. One big surprise that we found as we pulled off the first couple panels of that roofing to start to frame, tying in the framing of the new area, was that that metal roof was installed over strapping, 1x strapping, no sheathing. So we pulled off those first two pieces of metal, and we're looking at the fiberglass in the cavity. Now this house, the location is about the most exposed area you can find. It's in the middle of a wide open field in a mountain valley. The wind just whips right on through there like nobody's business. So it's been an extremely well ventilated home to this point. But we're changing that. So one of the aspects we had to combine into this was us putting sheathing on that roof assembly as it exists. So we actually put the OSB directly over the strapping that is there. And that gave us the added benefit of being able to add a little extra insulation above the fiberglass that's in place. We are dense packing above the existing fiberglass. Basically, the gap between that fiberglass and the bays to the underside of the sheathing at this point is about 3 inches. So we're going to be able to dense pack 3 inches over top of that fiberglass. There's a technique that we've done quite a bit in retrofit work, going and doing our home performance with EnergyStar contracting, coming into homes that have minimal insulation and sloped assemblies. And we're able to dense pack over top of what exists, as long as there's no, in the end, there's no connectivity between the fiberglass to the roof sheathing. If we can get a substantial layer of cellulose over top of that fiberglass, we can feel confident that we're not going to get any moisture drive or condensation issues to the underside of that roof deck. Plus, in this situation, putting that 3 1/4 mineral wool over the top should keep that sheathing in the temperature range we want it to. So, obviously, from the construction standpoint of the existing house, that's a pretty good indication of where some of the corners were cut to bring that cost down to $50 a square foot. And one of the corners that we had to cut as far as the construction specs for this project were the windows. We tried to do triple pane and directional glazed glass as a part of the work scope, but that was something that the homeowners decided they would rather eliminate that and put the money into some other aspects of the building. So unfortunately, we are back to your standard low E insulated glass windows, 0.3 LU value. And you know, these are, obviously that's something that we would have liked to have seen as a part of the whole work scope, but ultimately, in the scope of this presentation and my approach to a project such as this, we have a passive house standard that we know we can build to, but if we're going to try to make this type of construction more widely available, what aspects of the passive house package do we know do we know that are elemental and we need to incorporate into any project? And I guess I'm leading to, at this point, until we can get some other options available in the marketplace for windows, I think windows sometimes are going to be that compromise when you're talking about a retrofit situation, or when we're looking at the budgetary effects of doing what we want to do with the building shell. So in this situation, that certainly was a compromise, and perhaps the biggest one. So our desired outcomes, we want to get maximum air tightness in the new construction and improve the existing building shell as much as possible by doing everything that we're doing to the existing building shell, by taking the siding and the house wrap off, sealing all of the seams of the existing plywood, cutting off connections from the rafter cavities to soffits, and just a general thoroughness of detail around the existing building. We're going to, I think, become pretty close to achieving that air tightness on the existing section, and for the new section, as we go through the details, you'll see the effort we put into making that airtight. Accomplish maximum R values throughout, given budget realities. Eliminate thermal bridging as much as possible. Again, the new areas, the details that we put into that, confident in our ability that we've done that on the existing home. There's some areas that we just don't have control over that we're going to have to live with, but you know, we've made a substantial improvement on those existing thermal bridging. Fully ventilated wall, rain screen, and roof drainage plane. One of the things that we came to in the process of this, and I know some of you today are coming to this presentation using mineral wool, rigid mineral wool on the exterior of the building as part of those. Maintaining a vapor open exterior assembly, to me, was crucial on this project, and that is how I came to the point of using the rigid mineral wool for this project in place of foam. And that was the original discussions at the beginning of the project, was to use rigid polyiso over the whole building to boost the R value, cut off that thermal bridging. But I wanted to maintain a vapor open assembly in this process, so that is why we chose to use that mineral wool as a major component of the decision of that. We want to reduce the existing blower door numbers, the existing air tightness now as much as possible, and provide maximum flexibility for future upgrades to heating and electrical supply for the home. So, to me, this is a philosophy I want to take to any project that we work on. What dynamics can we do to a building that can make it flexible for new things that can be applied to heat or provide electricity to that house? And obviously, one of the things in this is air heat pump. You know, I think we should be accomplishing as best as we can on our existing building stock to make them not just do minor improvements that you know you can justify easily, but to go beyond to the next step to make those buildings more adaptive as things change down the road. And obviously, these air-to-air heat pumps are, to me, the great next step, especially if you want to be achieving something near a net zero type structure. You start to build a house that has this little required energy input, and you can much more easily adapt a renewable or alternative energy system to that building if you're able to shrink down your loads as much as possible. So, structural details. All framing for the new area was 16 on center, and that continues from the rafters all the way down to the foundation. I was looking at doing 24 on center to start, but what one another aspect of this is trying to find ways to streamline this process to make these passive house type goals more adaptable across a broader range. So at this stage, and with our crew and trying to work through all the different steps and details that need to be attended to get things done right, we said, all right, let's keep things simple. Go keep it at 16 on center. We can more easily fit in all of our window layout and everything that was drawn into this, and we can streamline that aspect of things. So we stuck with 16 on center, but eliminated any unnecessary blocking and framing. Really appropriately sized window and door headers. The window and door headers have been overbuilt for a long time, and we got. I basically took the information and feedback of the structural person I work with at our building supply place and downsized his opinion by a certain percentage. The same concept of upsizing everything. So I'm confident in how we structurally put together those assemblies. Thermal boundary of the building defined by the 2x12 rafter cavities. That is the roof assembly for the new section of the building, as well as the existing. So that's our thermal boundary throughout. We framed our roof so that the rafters are cut flush to the top plates. Our sheathing, wall sheathing is run past, nailed off into the ends of the rafters and connected to the roof sheathing. So there's no overhangs, there's no eaves built in the framing process. Those are being applied after we put on our rigid insulation and our drainage plane. And the ability that we created with that is we now have continuous ventilation all the way from the base of the wall up to the ridge of the building, because we've laid out all of our framing, 16 on center, all of our strapping for the drainage plane is 16 on center. The roof assembly is a ventilated roof assembly, 2x4 sleepers laid flat on the roof deck, and another layer of 5/8 OSB put on top of that that is what our roof is applied to. So we have continuous ventilation from the bottom of the wall all the way up to the ridge cap, behind all of the overhangs, and everything. So to me, I was kind of excited about that aspect. Okay, this is pretty cool. We've got this constant ventilation loop behind the rain screen for the whole building. One of the things that you'll see in the next couple slides here is structurally how we had to tie together the second floor and roof of the new section of the house to the existing by transferring rafter loads to what was a non-bearing knee wall in the existing house. We wanted to be able to frame this in a way both from a cost standpoint and then also from a just functionality standpoint for the homeowners. We didn't want to have to kick them out of the house in order to tie the new section to the old. So we did some things structurally to accomplish that. New standing seam roof installed, and again the party plank and one by finger joint behind the exterior. So our foundation originally we had proposed a super insulated floating slab foundation, putting 8 inches of EPS foam down 3 feet past the perimeter of the footprint of the foundation, and then using ICF forms to form up the perimeter of the building, and then backfilling in between. We ultimately ended up settling on a standard frost wall foundation, dug down to 5 feet depth, set our footings at that, and then poured a frost wall up flush to the existing height of the foundation of the existing house. Cost-wise, this was a consideration. We took this approach and then put 3 inches of XPS foam on the exterior of the walls, full height. We have 2 inches of XPS below the slab, and a complete vapor barrier sealed all the way throughout that over top of that foundation and beneath the slab. One of the things that we did to seal our sill plates to the foundation was to use an EPDM rubber gasket. And 2 layers of it, one on the inside, one on the outside. This stuff was great. It really has a lot of flexibility and compression, and obviously we know that EPDM rubber is going to stand up better over time in regard to it does not have a memory, so as a seasonal movement does occur, that gasket is going to remain flexible and keep that gap sealed tightly. The manufacturer of this material does have a single layer gasket, basically for a 2x6 plate. I decided to go with the 2 smaller ones, one on the inside and one on the outside, kind of a redundancy. So that was something we incorporated on this, which we had not used before. Structural details. So this is going back to what I just spoke of. There's your that's your roof assembly. That's what we found when we pulled off that metal. Like I said, exposed fiberglass to the underside of the corrugated metal roof. And this is what I spoke of as far as trying to avoid disrupting the whole second floor of the house, again from a cost standpoint, and then from not kicking their family out of the house. We headed off the rafters to bear on the knee wall. The knee wall we sheathed with 3/4 inch Advantech to make that a shear wall, to help transfer some of the load of those rafters. And then the exterior walls of the new section, you can see at the base of the wall there's a micro-lamp header that runs 4 feet into the knee wall and then 8 feet passed out into the new area, so it's a 12-foot long header. And what essentially that is doing is helping to transfer the load of the rafters that are coming down into the valley from the new ridge beam to these exterior walls. It's helping to transfer the loads that would be point loads on the old rafters that we cut off, helping to transfer some of that load onto the new wall area of the exterior wall. So in doing that, I felt confident that we not put any undue stress on that knee wall, because that knee wall sits again 3.5, 4 feet in the exterior wall of the house. There's no support beam or anything underneath that on the first floor. First floor of the existing house is wide open. So, And doing that header and then creating a shear wall out of that knee wall, we felt that we've accomplished the transfer of load enough to be able to do what we did. So this is framing of the new sections. As the only thing that's missing at this point was the fully sloped returns at the very gable end. So now moving on to our air sealing insulation details. We focused on this. I think some of you were here for a presentation Ken Levinson did a few months back from 475 Building Performance. I've been kind of following their company and their products since they started about a year and a half ago now, and decided to use the ProClima series of weather-resistant barriers, house wraps, tapes as our primary air sealing and moisture barrier strategy for the whole building. So this is what we're applying to the new section and the old. We've been using pressure-sensitive acrylic air sealing tapes throughout. We've sealed the when we stood the exterior walls onto the floor decks, we sealed the bottom plate to the rim joist and to the sheathing of the floor deck with pressure-sensitive acrylic tapes, as well as gluing those bottom plates to the new floor deck. We've glued all of the sheathing of the building to the framing. So every single, framing member that sheathing contacts has been glued. All the tape, all the seams, all the plywood on the exterior of the building have been sealed with this tape. And the tape's been great. We've gone through a ridiculous amount of it, and spent more money on it than I ever would have wanted to on tape. But it's great. I mean, it's once you put it on and that stuff sets for about a day, you're not ever pulling it back off. And it's very flexible, so we can stretch it around gaps. They make different types that have different properties, but essentially all the tapes are vapor open. As far as durability goes, they're guaranteed to have a 60-year life cycle as far as being adhesive. So we've used that on all of our details throughout. The one thing that we did not do, which we could have done, is tape all of the nails that we, all of the spots that we nailed our sheathing to the framing. Ideally, I would have wanted to tape all of those, cover all those nail holes with tape also. That is one thing we had to eliminate out of the whole scope of things, just simply from a cost standpoint. But knowing that we glued all of the framing members to the sheathing, that to me is a little extra insurance. We may have the nail holes still exposed, but they've been glued, so I think we can feel pretty confident about that. So we still use some single part foam and caulk where we needed to in places that we had larger gaps or we needed some flexibility in the joint. We just went over the R values for the foundation. We have an R36 assembly below the finished sunroof slab, and the next slide is a detail of that assembly. R32 is our overall value of the exterior walls for the new area. R31 for existing, taking into account the R value of that fiberglass. So that's dense pack in the walls with 3 inches of removal on the exterior. We were able to accomplish R60 in the existing roof plane. The 9-inch fiberglass pads that exist, dense packing 3 inches over that, and then the 3 1/4 top rock BD, Roxel. All the mineral that we use is Roxel as a manufacturer, and the top rock DD is what we put on the roof deck. And on the exterior walls, we use what's called Comfort Board IS. They have 2 different densities. The top rock is a commercial roofing insulation. I'll go over the densities here in the next couple of slides, but that stuff is, you can stand on that and it won't deform. The exterior, the wall insulation is a little less dense. but we haven't been having too much trouble with putting that up as far as compression goes. There's been some research done by Building Science Corp, I know, on the durability of installing exterior cladding or vertical 1x3 strapping on the same 3-inch depth of the comfort board on the walls. There hasn't been any issue with the strapping or the fasteners sagging, as a result by you going this approach, so we felt confident in that. And then the new roof deck, we're about R57, given the 11.25-inch cavity of the 2x12, and then that mineral wool over the top. So this is the detail of the floor assembly below the finished concrete slab of the sunroom. We have 3-inch core over radiant tubing, and that's our finished floor surface. So what we did below, again, this is the exterior wall, ranges of roof, foundation wall, and slab, for the thin area of this foundation, which is XPS and that. And then in between the double 2x10 strip down to 9 for wall height. I'm away from the microphone. Carry it around like a rock star. And what we did is between each of the joist bays, we started off by putting a 3/4 nailer on the bottom of the joist to support 2 inches of polyiso that we then sealed to that little flange with some silicone. Then dense packed the remainder of the joist bay, cellulose, put down our 3/4 inch decking, 2 inches of high R on top of that, the radiant tubing stable to that, and then slab poured over top of that. So an overall R value of R36, eliminated the bridging. We have the reflectivity of that polyiso for the slab above. So this is dense packing and floor assembly prior to standing the walls. So here's some pictures of our framing details. Again, all the OSB seams taped. One of the things that we did a little bit, you have to do differently with this to avoid using a primer for the tapes, is with the OSB, you got to flip it over and put the smooth side out. The tape will stick to the textured side of the OSB, but it sticks much better by using a primer on that textured side. But if you put it on the smooth side, we haven't had any problems at all. So all of the OSB that we put on the building was put in the smooth side out. And we did choose to use OSB on this over plywood or CDX, which I would have preferred to use, but again, it's a cost consideration. So I've seen so many buildings in our energy auditing and retrofit work that we do of just OSB, and even on this house that is just mulch beneath the siding from moisture drive through the wall assemblies or sun-driven moisture drive on south-facing assemblies, window openings. That's again the reasoning behind using these weather-resistant barriers, tapes, and everything that we did. Is the weather-resistant barrier that we're using over top of all this OSB is vapor variable. When we have pressure drive in the heating season, pushing moisture vapor outward, that barrier is going to be allowing for drive and drying to the outside. That mineral wool is vapor open, so any moisture that makes it through the wall is going to dry to the outside to that rain stream. In the summer, if we do have cooling within the house and the pressure differential is the opposite, that same aspect occurs in that house wrap, that it will dry to the inside. Not as concerned as that, obviously, for us around here. They won't be using any cooling as far as I know, but we know that we have a fully vapor open wall assembly in doing this. Again, gluing all of that sheathing to the framing. So again, all the seams, including intersections of wall areas, roof planes. We did use, again, some single part to seal some larger gaps, but very, very little. I mean, that ridge right there was one spot, and then the only other spot that I can think of off the top of my head that we did use it was to seal the base of the mineral wool before we put it on the exterior walls. I'll show you that as we get a little bit deeper on here. So again, this slide on the picture on the right that is the wall of the new area connecting to the roof plane. So that's your roof sheathing, wall sheathing, that intersection taped fully, that seam. And we will be applying our eaves and our overhangs to that once we get all this rigid mineral along the walls. On the interior, these are some images of the second floor of the new section of our interior air barrier and our thermal boundary defined for the interior. By doing what we did with using that 2x12 cavity as our thermal boundary, we're able to eliminate any penetrations to any of that assembly or wiring or any interior chases at all. The blue air barrier is a ProClimate product. It's a vapor open interior air and moisture vapor, or air and moisture vapor barrier. Honestly, it's been awful to work with. It's a paper-based material. You can use it in place of InsulWeb for cellulose. So I said, oh great, we get an air barrier, we get our backer for our cellulose at the same time. But man, I mean, you look at that stuff crosswise and it'll tear on you. Just stapling it, it's been tough. So I don't think we'll be going back to that one again. Sorry, Ken. But I know they have a different product available that is a little more reinforced. But what we're able to accomplish, though, is that whole rafter plane is fully sealed now with this air barrier. Our ceiling joist, because we have a 20-foot wide span of this room, we have 2x6 ceiling joists that you can see we cut the angle to the rafter, their alignment with the rafter. We use timber log screws to screw the ceiling joist into the bottom of the rafter. And then on the right, we applied a nailer perpendicular to the rafters and then hung vertical supports to help take out and avoid any sag of the ceiling joist in that 20-foot span. I didn't see any real threat of spreading of this wall assembly, given the 2x12s and the roof pitch, but the collar ties with these timber locks are still going to resist that outward thrust if there is any, and we keep that that insulation boundary intact. All of our wiring chases and everything are going to be run up above those ceiling joists and through interior partitions. So this is our exterior wall assembly. Just to go over this real quick, 2x6 construction, dense packed cellulose, 2 layers of 1.5 rigid mineral wool, the strapping, and then our siding. I decided to go with 2 layers of 1.5 for 2 reasons. One of them being ideally, trying to do exterior rigid insulation of any type. If you can overlap the seams, all the better, rather than having one single layer of 3-inch and then you have a potential gap at each of those seams. So that was one of the reasons for using the 2 layers of 1.5. But it also provided us the opportunity to have an easier window installation. So what we did around the windows was we have a continuous layer of 1.5 going all the way around, and then at the window rough openings and door rough openings, in place of putting that second layer of 1.5 butted all the way to the RO, we ran 2x4s and screwed those through the first layer of mineral wool. And now we have a nailer for our windows, our window flanges and door flanges all the way around. We still are accomplishing a thermal break there by that first layer of 1.5 of mineral wool. So we still have an R4 isolation from the framing of the wall assembly itself to the exterior. So to go over the cost and how this all broke out, for the walls, we ended up with needing 3,100 square feet of material. The one kind of rub with the mineral wool products is that 4x8 sheets don't really exist for whatever reason, part of their manufacturing process. The wall material that we were using was 2x4 foot sheets, and they come in odd sizes, like 2x4, 3x4, but 4x8, the only way you're going to get a 4x8 sheet is if you buy a whole tractor trailer load. And I don't have a whole tractor trailer project yet for that. So we're stuck with 2x4 foot sheets. The roof material was 4x4. The roof material that we ended up with, the Top Rock DD, which I think has been great. Honestly, I might even try to use that on the walls for the next project because it's that much more dense. I have the densities on the next slide, but the density of that top rock is more dense than the comfort board and even less susceptible to compression by driving your battens or otherwise through it. But the top rock, they manufacture and stock 1 and 2 inch thick of that material. But we ended up with 3 1/4 inch because what you can find, and when you call to order this stuff, you say, all right, have you guys made a run of any other thicknesses for other projects? Because again, this is commercial materials, so they're pumping out tens of thousands of square feet of material at a time for a project. And that's how we came by this 3 1/4 inch material, because they had an overrun of that 3 1/4 inch for another commercial project. They had enough square footage for what we needed. So we went with a single layer of 3 1/4 for the roof deck. So our total installation budget we had was $69.10. The comfort board I asked for the walls was 67 cents a square foot. What is that, 1911 and change. And then the top rock was $1.98 a square foot, and that's for that thickness. So, comparatively speaking, we're in a range that's similar to, say, Thermax for polyiso material. If you're going to be talking square foot comparisons for cost. We weren't planning on using Thermax for walls, but we were planning on using the polyiso before we got to this point of moving through the process and getting to the mineral wool. So, from a cost standpoint, it was still within the ballpark that we were hoping to be within. And then the big fun one was the $2,900 so far, building wrap tape. And you can see where my budget's at right now for installation. So, but that's part of the experience of this is, okay, what are we going to, it was trying to estimate how much tape we were going to need for this. Yeah, it was a joke. I mean, I just, all right, we'll start off with a dozen rolls. I think I got enough linear feet, and then we move on to the next dozen. So we've gone through a lot of tape. But I did build flexibility into the overall project budget. That fact that we're a little bit over on the installation shouldn't hurt us in the end. But to me, this is a project to give us an understanding of, okay, what's the real cost of this in the future. So comparatively, some of the things I looked at the beginning of this was, all right, for an interior air barrier, we can use that blue material that I just showed, the DB Plus, at 32 cents a square foot, which is kind of expensive, but alternatively, if we wanted to create an airtight interior barrier, we could use half-inch OSB. That's 40 cents a square foot. So, we're saving still by using that DB material. Installation-wise, it's been a pain in the keister, so we got to factor that into it too. So, but from just a raw material cost standpoint, that's still a little bit less than the OSB alternative. The TestCon tapes, again, a ProClima product that we went with, 36 cents a linear foot. Comparing that to some of the other options, as an apples-to-apples option would be the Wiggler tapes, which I'm sure some people are familiar with. That stuff's 85 cents a linear foot. So this ProClima product is still less expensive by a significant amount per foot on that. And then another product comparatively to that was a 3M 8076 flashing tape. And we use that to seal our vapor barrier to the concrete foundation. And that's the only spot I've used it in because that's not vapor open. It's in there, it's a vapor barrier. So I kept that to the foundation work, but that stuck right to the concrete. I mean, concrete that was 6 days old, it stuck right to it. So we didn't have any problem with that. But still, even that TestCon tape is less expensive than that 3M. And I've seen some projects over the past couple of years of trying to accomplish the exterior air sealing with using products like that 3M tape, using Vicor bitchethane type wraps, and I wasn't going to go that route because again, you do that, you're putting a vapor barrier, wrong side vapor barrier on that building. So we stuck with the vapor open material. And now, bottom here, the compressive strength. So that top rock DD 13.7 pounds a cubic foot versus 8 pounds for the comfort board. As a comparison, like Blue Board XPS, that has a compressive strength of about 20, 25 psi, depending on the formulation of it, compared to the 15 psi for that top rock. We are needing to do squash blocks in certain areas, like for the overhangs, the roof, the eave overhangs. What we're going to be doing for squash blocks for that is cutting 2.5-inch pieces of Schedule 40 PVC. And I can't take credit for this technique, but it's pretty cool. I found it online. Was using an air filter or an oil filter wrench, or automotive oil filter wrench that you can put on a 3/8 socket. So you put it in your drill, and what it is this spring-activated clamp, and it fits over a piece of 2.5-inch PVC. Turn the drill on, and it clamps tight to the piece of PVC, and you can drill it right through the mineral wool, flush to the sheathing, and it just you've got a plug there, and it doesn't take out any material, and then you just use that and fasten right through it. So that was pretty cool. So we're using that for squash blocks for the overhangs and all this, but again, putting on the strapping, we haven't had any real problem with as long as we're careful as we're screwing through that strapping, we're not having any real problems with compression throughout the wall. We're using 6-inch screws, 6-inch GRK construction screws, nothing special, no timber locks, nothing like that. So we were able to get those cost effectively, and those have been working out fine. So this is putting up the exterior mineral wool from the walls. What we were able to do is put up the first layer with 3-inch cap nails, just tacking it, 2 or 3 per sheet just to hold it in place. And then the second course of material, we use these insulation discs for commercial insulation or rubber membrane roofing applications with some 4-inch screws. And we only had to do the first course, basically, of the second layer. We were able to anchor that back into the rim board, essentially. And then from there, we were able to start stacking the layers on top of that, sticking a cap nail into the first layer. It wasn't going to the sheathing, it was just stuck into the first layer of mineral wool. And then we were able to start running our strapping up the wall and slide sheets behind it as we went. So it's gone pretty quickly, pretty smoothly. So again, you can see all of our wrap details sealed all the way around the whole building. Any penetrations through that, whether it's just a barrier, we sealed with pieces of tape as we went. As we started to move our little sticks on the roof or getting up the roof, we taped over those holes as we went back down. So this is the window rough opening detail. Again, you can see we have that thermal break existing between the window buck that we're installing the window flanges to and the framing behind it. The one funky thing about this that I'm still wrestling with is properly flashing the building wrap on these window rough openings. Because we have this window buck on the exterior, and you can't put any tape on this mineral wool. So you can't flash the window flange and the window buck to what is your drainage plane, which is the mineral wool, like you would want it. You can't wrap those window flanges to have something shedding over the top. But we have layers of redundancy in this. We have 2 layers of material that will shed and drain water. We have the house wrap behind, which will drain water. We have the drainage plane of the 1x strapping behind the siding, which will direct the water. So we carefully, as best as we can, sealed all of the building wrap on the framing window rough opening. And then as the windows go in, we will be sealing the window flanges to the window buck with the air sealing tapes, and basically relying on that to prevent anything from coming behind the window flange. So to me, that was a compromise, but I did a lot of reading and a lot of researching around to find out people who've done similar methods to this and seeing if that was a problem or other flashing details. One of the things I was considering doing was actually getting a deck ledger flash which would have an 1.5 inch overhang, and putting that over the window at the top before we put the second layer of mineral wool on. Ultimately, we ended up skipping on that step. So I still feel confident in how we've wrapped this. I don't think we're going to have any problems with water infiltration at these openings, but it certainly is something that was strong in my mind as we went through this. And man, part of it just doesn't feel right. But anything new, you got to just, I guess, sweat through it and see how it goes. But one important aspect around all of these openings was sealing the building wrap to the framing, because unless we did that as it's shown here, then we have some openness behind that weather-resistant barrier and the framing beneath it. So all of that weather-resistant barrier is sealed completely around the whole building shell. And that is really what this all comes down to. There's some things we could have done a little bit more, like taping again the nail holes, but we've got multiple layers of redundancy from an air sealing standpoint. Gluing of the sheathing, taping of the seams, that weather-resistant barrier, sealing all of that. So I feel pretty confident in what we're going to be able to accomplish by how we've gone about it. And this is one of the areas where we did use some spray foam. We did not tape the bottom of that weather-resistant barrier to the sheathing beneath it at the base, stapled there. So we used the single-part foam as we were putting up the first layer of mineral wool to essentially seal that building wrap at the bottom of the wall. So that cuts off our airflow behind any of that house wrap at the base of the wall. So just here's a couple, this is about where we're at right now. We're starting to put the rigid mineral wool on the roof and starting to build the overhangs. Roofers are coming Monday, so we better be done with that area at least by that day. You can see the window detail on the right. Now, this is a project we did last year. This isn't obviously the roof assembly we're doing, but I wanted to show an example of what we're talking about for this ventilated roof assembly. So in this project, we put 2 layers of 2-inch high R over the roof deck, and then 2x sleepers. And what I wanted to show here was this is essentially what we're building in this project, but using the mineral wool. And the sleepers overhang the fascia by about 2 inches. And you can see those 2x slip down into a little pocket of that metal right there. And that is perforated. That metal that those 2x slip into is perforated at the bottom. So when the roof sheathing goes on, you have ventilation beneath that the gap between the roof deck and that 2x and the insulation below. So we have a ventilation channel essentially underneath all of that new roof deck. This I just dropped in there as an example of the Roxol material that we use. So, you can get different. There's many different types of rigid Roxol product available, different densities, different properties. That Top Rock DB Plus on the top right there actually has a bituminous type layer as a part of the top layer of the material that you can rubber roof right over top of. So there's a lot of options in the types and density of the material that you can use. But so far, I've been quite happy with it, and it's gone quite smoothly. I mean, it goes up quick on the walls. And like I said, there's some details you got to be attending to as far as making sure you're not overdriving fasteners. But as long as you work through that the first day or so, then things go pretty smooth from there. And then that brings me to our next adventure, which we'll be doing in the spring. This is a lodge in Belmont that was built by Paul Thayer, who was an architect who designed a lot of the Green Mountain Club buildings and lodges back in the 20s and 30s. It's this gorgeous lodge / summer residence in Belmont, but the only thing separating you from the outside is 3/4 inch of pine around the whole building shell. So the new owner who purchased the house wants to turn it into a year-round home. They do not want to touch the interior at all. They want to leave it exactly as it stands. So we're going to be adapting this process to this project by building an exterior wall assembly over the existing building and doing the same drainage details, the same roof overhang details, the whole 9 yards. on this project, so pretty excited about that going down the line. So that about wraps it up. Anybody has any questions?
I'm just going to check to see if anybody online has a question as well. I'm taking questions. Anybody have any questions?
So the Barclay mixture and all that, very plain to business.
It has very, very low moisture absorption, like 0.3 firms, but as far as vapor transmission, it's virtually completely vapor open. So it's similar in regard to how cellulose will work. You know, if moisture does get into the material, if any moisture is drawn into it, it's hydroscopic, so it'll disperse and then dry quickly to the outside. What we found with some of it, since we've had some rain here recently, and it's been shedding over the building, cut through the material, and it's quite wet on the outside, but it's only wet like that deep into the whole, 3 inches of material. So it's just, it can get wet to the outside, but it dries quickly. But driven water, raining, like if it's raining and the wind's blowing the rain against the mineral wall, it beats up, just runs right down.
There's a question here from Peter Mandata. Sorry if I'm not pronouncing that right. The mineral wool folks tell me they do not approve it for this type of application. How was it structured?
I'm a rebel.
He's a rebel.
There's been if you start digging around online, there's many people who've gone this approach already. And in a commercial situation, this is a typical application. Roxel's manufacturing facility, I don't know where it is. One of the European ones. I got quite a few of them, but one of their manufacturing facilities, they mocked up a whole wall assembly that's fully exposed. Exactly like this, 3 inches of rigid material on the exterior of a commercial building, a drainage plane over top of that, and then it's basically just got glass over it. So it's fully open to the elements, and they've had this thing built for I don't know how many years. So, I think a lot of this does go back to the same thing my heating contractor did, is cover your butt, and it'll work, but they're not always going to say, this is definitely the way you can go about it. Like the roof assembly was one of those situations. Talking with the technical people at Roxel about how we were going to be building this roof assembly, there's no water that's going to be getting to that rigid mineral wool beneath the roof deck above. But there's no reason to have any lack of confidence in its ability to function if water did get behind there. It's still, they didn't manufacture the material to beat up water and drain it for no reason. It's a property of the material that is a benefit in its function. So I feel confident in the assembly, and I don't think we're going to have any problems.
Just wanted to say to David Benjamin, if he's still on, the webinar is being recorded and will be available later. Dale Bickenbach says, Roxel is Rockwell as far as I know. Is this really mineral wool? They're actually synonymous names. It's all a product that's made from slag left over from the steel making process. What are you doing for a termite shield? Asked Carol.
Well, I'm going by Joe Lisbrook's opinion that insects don't eat rocks, so they won't eat mineral wool. To be perfectly honest.
I think they're talking about the XPS below grade. Yeah,
that's going to be fully covered with or Durarock type product in the end. So that'll be fully covered.
Okay. Please repeat the question. The mic. Oh, sorry. Will you be doing a blower door test soon?
Yeah, once we get our windows and doors in, we're going to be doing zonal testing of all of the new areas. So basically, blower door of the living room space, first floor, blower door of the sunroom space, blower door of the second room areas, and then again isolated blower door for the existing home, and then the whole thing. Right. So we're going to be doing plenty of that as we go through.
Okay, last question here I have online, and then we can ask again here in the hall. How close to the pH standard for heating primary energy is the project? So the question first is, did you model this?
The answer to that is no. No, I am not a certified consultant, and it's a goal for me, but I've not gotten there yet, and we did not have anyone who basically, we didn't enroll the project in any way with someone to do that. So if anybody here wants to have a little test project,
for free.
No, so we don't have that information, and you know, for me, again, what I'm trying to distill with this project is the most elemental and most important things that are going to accomplish durable and efficient buildings and structures that are going to last for a couple hundred years without any major changes.
Or at least until the tape wears out, right? The 60-year.
Right.
David.
You did a great job there. So like exterior, like, you kind of missed something, but you're also putting air barrier on the inside.
So the question.
I was wondering what you're thinking of air barrier.
The question was, we saw air barrier work on the outside, and is there also interior air barrier work?
Correct. Yeah. That DB product, the blue stuff on the roof or the underside of the rafters, that's our interior air barrier for that assembly.
That's what I was wondering. You think how much what was your thinking behind that air barrier system already created?
From the exterior, knowing that we had to put all this detail into the exterior. Basically, we knew that we were going to need some type of interior moisture vapor barrier as a part of the interior detail. And for the roof assembly, we weren't planning on drywalling the underside of those rafters, because they're going to be above the ceiling plane of the room. So that's why we chose to use that material on that plane. For the exterior walls, I was considering using this on the wall areas also behind drywall. But we're going to just simply be gluing the drywall to the stud and using our latex plate as our moisture vapor barrier essentially on the inside. So for me, it was trying the product approach and systems approach of the ProClima series of products essentially. This was their product for an interior barrier, and we were trying it and see how it went. And again, that's one I'm not going to go back to. Well, we may try the other product that has a similar. That can be used for the same thing, but it's a little more durable, I think. So
the Intello 100, the one with the white one.
Yeah, the Solitex. Yeah.
Carol has another question. Who manufactures the EPDM sill gasket? That's a cool process.
Where did I find that?
That was the sill gasket that
it was online building. I can't recall. I couldn't find it. There was only one place online I could find it. They're kind of a specialty building products distributor in the Midwest, and it's going to fail me right now.
Okay,
there you go. Just popped up. Conservation Technology.
Thank you, Ginger.
So there you go.
Fantastic. Any other questions? Okay, Steve, thank you so much for this great presentation.
Thank you.
And I just wanted to say we're going to be stopping the presentation recording, and we are going to leave the webinar on for people who are interested in participating in the Passive House Alliance U.S. Vermont Local Chapter meeting. Those who are not going to be staying for that, thank you very much for coming. And the recording, as I said before, will be posted online within the next week or so. And so if you're interested in having that, then you can go to the national website. And we're expecting the local website for local Vermont Vermont, the Tea House Vermont chapter to be up and running sometime in January, so we'll have all of our presentations there as well. Thank you very much, and have a good day.